We're going. It is blinking and there's a timer counting up. I think we're going. Probably. Hopefully we have audio. Otherwise, this is going to be really awkward. I'm Ray Scheifler with Area515. This is a silly electric vehicle class. This is less about building any individual vehicle and more about background terminology and decision points that you need to make when you are building a silly electric vehicle. Also, this presentation is going to focus entirely on the electrical side of things and not talk about the mechanical side of things, except briefly when we're talking about motors, because motors are a hybrid electromechanical thing. But I'm not going to get into things like steering or brakes or not killing yourself on a bicycle. I'm just going to talk about electrical stuff. So I'm really going to focus on three major areas. I'm going to start with motors and motor controllers, and then talk about batteries, and then some about safety, because apparently safety is kind of a thing. And then I'm going to finish up with some case studies. By case studies, I mean talk about vehicles that I've built previously. So, motors and motor controllers. Some fundamentals, just really basics here. Current flowing through a wire creates a magnetic field. Magnets like to attract. North attracts south. If you reverse the current, the magnetic field that gets created also reverses. So motors are all based off of magnets chasing magnets. One of the magnets happens to be an electromagnet, the other might be an electromagnet, might be a real magnet. But it's all about magnets chasing magnets. Technically, there is no such thing as a DC motor. If you were running straight DC through something, it would lock phases and it would sit there. So in actuality, all motors are some variant of AC, and that there is something that is causing the currents to reverse. The big difference between a brushless and a brush is whether that's a mechanical thing causing reversing or a physical thing. The other fundamental point to mention here is that if you have a changing magnetic field around a coil, it induces a current. Now, whether that is a fixed magnetic field and moving a coil through that, or whether that is a magnetic field that is changing in intensity and moving, that either of those induces currents. That's going to become important here in a bit when I start talking about back EMF. But fundamentally, a motor and a generator are two sides of the same coin. Either you are running current that causes a magnetic field and you're chasing magnetic fields, or you've got a moving magnetic field that's inducing current. So again, this back and forth interplay is kind of important. The final fundamental that I kind of want to talk about here is timing. Just like in a car, you can have timing advance or retard on your spark, whether you spark at top, dead center, or after. When you switch your magnetic fields, kind of matters. If you switch it, if you're trying to optimize for high speed, you want to retard your timing, so you want to switch later, because there's inductances and there's slop, and it takes time for the field to reduce. And so, depending on your motor, you may or may not have the ability to time it. On a brush motor that is physically rotating the commutator housing, the brush housing, so that the brushes sit physically different. You're mechanically timing it. On a brushless DC, that may be either adjusting your magnets so that your magnets aren't, adjusting your Hall effect sensors so your holes aren't exactly aligned with your magnets. But you can play with some interesting things with timing to either optimize for low speed, high torque, or for high speed operation. Again, interesting little fundamental, not necessarily applicable to everything, but kind of a cool detail. Some terminology here. Stators are stationary. Traditionally, if you look at a motor, the outside casing that has the magnets glued to it, that's the stator. It's stationary. The rotor is the bit that rotates. And that's the thing that is actually connected to the shaft that is spinning, that is causing the torque. Just kind of useful to know those two terms. Not really a term here, but voltage equals speed.
The higher the voltage that you have, the faster that the motor will spin. Conversely, current is equal to torque. The more current that is flowing through the motor, the stronger the magnetic field, the more torque that you have produced. And power is voltage times current per Ohm's law, which is also, coincidentally, speed times torque. Again, there's some scaling factors here. But this is how kind of everything relates together. The other key terminology here to talk about is back EMF. Back EMF is the voltage that is induced by the fact that it's a spinning thing. So at rest, there is no back EMF. You've just got your battery and a resistor and you're running current through it. When it's spinning, the motor is generating voltage which is fighting against the voltage that you're trying to put into it, and that reduces the amount of power. There's a couple of key metrics or key words that you see when you're talking about motors, and that's either their kV value or their kT value. And those are, the kV is RPMs per volt, which is to say that if you were to hook a X volt battery up to this motor, it will spin at X times its kV value. KT is a measure of Newton meters per amp. So it's a measure of how torquey the motor is. Incidentally, kV equals 1 over KT. They're inverses of each other. You either have a torquey motor or you have a fast motor. And you really can't get around that. I mean, you can apply more power to the motor, but you either have high speed, low torque, or you have low speed, high torque. They're really fundamental inverses of each other. A very simplified motor diagram is that you have some external voltage source going through some resistance being fought by the back EMF force. The resistance here, the big difference between a low power motor and a high power motor is what this resistance is. On a low power motor, that's going to be a relatively high resistance value, and that really just limits how much current can I shove through this motor when it's stationary. The lower the resistance is, either because you've got fewer turns of wire or you've got thicker wire, and internally, I'm talking about the magnet wire on the windings. The lower the resistance value, the more current you can shove. The other thing that's here is the back EMF generation, which voltage, which is also known as EMF, and so that's why those are kind of interchangeable. E or V is your KE times your omega, which is your rotational speed. So there's some constant for a given motor, there's some constant that you multiply by the RPM, and that gives you your back EMF. And so really what this says is at rest, this is going to be 0. Your voltage applied is all going through the resistance to cause torque, and you get lots of torque at rest. As the thing spins up, your back EMF increases, and so your Vn minus your back EMF is what your actual voltage is, and then that's divided by the resistance to know what your current flow is. So what this all kind of boils down to is, at rest, you've got all of your torques that you can have, and at maximum RPM, you've got none of your torques. So you really want to find the sweet spot in between. Also, I should have mentioned earlier, if anybody has any questions or wants me to go into more detail about things, ask, stop me. I am probably oversimplifying. One of the hardest things is knowing what I know that other people don't know and what details they might actually want. So, is there any, yeah?
Are we going to be able to get that slide business again today?
Sure. I can send out a link.
Yeah.
It's not a very pretty link, but I can send out a link.
I want to get it.
It's all black and white text and all sentence fragments, but yes, I can send out a link. So, we talked about some of the terminology, some of the basic fundamentals. Now, we're really going to start getting into motor types. I'm not going to talk especially a lot about motor controller types, because you buy the motor controller for the motor. You don't put a brushless motor controller with a brush motor. You just don't do that. Buy a brush motor controller for a brush motor. Within motor types, there are two fundamental splits. There are brushed and there are brushless. The difference between them, again, going back a few slides where I said that there is no such thing as a DC motor, it's all AC to get magnets to chase magnets. Do you have mechanical commutation or electrical commutation? And this all harkens back to, is copper more expensive than silicon? That's where a lot of these decisions start being made. And so back in ye olden days, and by ye olden days I mean 50 years ago, silicon is hella expensive. Copper is not expensive. You build brush motors because they are simple mechanical devices that you can actually manufacture. And in fact, they didn't have motor controllers on some old school forklifts, like forklifts from the 70s. They had relays. You clunked on a relay, and that connected the motor, and the motor spun. When you wanted the forklift to stop moving, you unclunked the relay, and the thing stopped. You also did such silly things as have a bunch of relays so you could connect one battery, or two batteries, or three batteries, depending on how fast you wanted to move. And so you had a series of relays that you could either engage one, two, or three batteries. They didn't have motor controllers because silicon was expensive. Then you start getting along in the years and you say, well, okay, silicon's getting cheaper. We can actually do some analog control with silicon. So now everything is pretty much switching PWM and MOSFET, so you actually have analog control. The other thing to consider with motors is that motors are, a really important characteristic of a motor is its magnets. Well, big magnets are expensive, so you take shortcuts, you cheat. When you're talking about small motors, you're probably going to run a permanent magnet, because that's easy. But when you get up into big motors, like you need for traction applications in vehicles or in forklifts, those magnets would be prohibitively expensive. Well, again, going back a few things, if you run current through a wire, you get a magnet. And so what you get are series or shunt wound motors. A series wound motor is a motor that's designed to have its stator coil in series with its rotor coil. And you actually just, some series wound motors are actually 4-terminal motors, and you have to manually bridge your series connection. Some of them are 2 wires, and the series is done internally. Interesting note, with brushed motors, if you swap the polarity, a brushed permanent magnet, if you swap the polarity, you swap the direction. Because now when you put current through, instead of having north-south, you have south-north, then it goes the other way. However, you should really only go one direction with your motor, because the mechanical interface of your brush on your commutator will wear in a particular way and can actually cause a rather sharp edge going the other way. And if you switch directions a lot, especially if you're abusing the shit out of the motor and you're pushing its limits, you really, really want your commutator interface to be good. So you really don't want to reverse that. But with a series wound motor, if you've only got 2 terminals, you can't reverse it. You apply power, it spins. You reverse the power, it spins the same direction, because double negatives. Because you reverse the outside and the inside, and so a negative and a negative, hey look, it's positive again. So series wound motors you don't really reverse. Again, you can actually get a series wound motor with a complicated pile of relays and actually be able to reverse that. There are forklifts out there that are driven off of series motors that do have reverse by funking some relays. It works. The really interesting thing about series motors is that with series motors, since the same current is going through both coils, when you are stalled, when there's no back EMF, you have really strong magnetic field on the outside and a really strong magnetic field on the inside, and so you get shit tons of torque, all of the torques. The problem with series wound motors is that as they spin up, there is less current on the inside and less current on the outside, and so there's a weaker magnetic field, and so you don't get as much back EMF. And so series wound motors, if they're not connected to a load, can grenade themselves. They can spin so fast that they fly apart. That's bad. That's really considered a bad thing. So you really always want to make sure that you get a load on your series bound motor so it doesn't, spin itself to death. And death on an electric motor is probably around 10,000 RPMs. That's when things just kind of start being too fast and not really wanting to be happy with themselves. Smaller motors can generally spin faster because they've got smaller bearings and just things are smaller. Bigger motors, yeah, you 10,000 RPM is pushing it. If you've got any amount of wobble in there, that's just going to rip the thing apart. Not bad. Shunt wound motors are what happen if you say, well, I don't want to put these in series, I want to put them in parallel. They have a very interesting characteristic that they really want to spin at one speed, regardless of their load, which is very handy for such things as an air conditioner in an electric vehicle. Not so handy for such things as a traction motor. The cool thing about a shunt motor is that you don't actually need a speed regulator on it. You apply voltage, it spins at an RPM, you can connect a clutch and a load, and it'll continue spinning at the same RPM until you seriously overload it and then it can't keep up. But we'll just not worry too much about that. The final category of brushed DC motors that I'm going to mention is the SEPEX motor, which is to say, well, let's not put the electromagnet coil in series or in parallel. Let's drive it separately. Because, sure, the interesting thing to note here is that in order to drive a permanent magnet or a series bound motor one direction, you need one FET. You need one switch to either turn it on or turn it off. To drive a permanent magnet motor in both directions, you need 4 FETs that need to coordinate. And so naturally it's 4 times more expensive to build one of those than one switch. And again, each of those 4 are going to have to drive all of the current that you actually want to run through the thing. And so again, in ye olden days where copper was cheap, silicon was expensive, they said, yeah, no, we're going to go one direction. If you want to go the other direction, we got 4 relays to take care of that for us. SEPEX motors were kind of an interesting footnote in that the main power that's going through your rotor is controlled by one FET. You only need it to go one direction. The other field that you want to switch, well, it's a relatively small field. Now, you're talking like 400 amps on the main and 10 amps on the secondary field because of how you want it. And so that means that your thing that you need 4 times as many FETs, well, it's 4 times as many small FETs and not 4 times as many big FETs. And so that's where SEPEXs came into play, because they were a cheap way that you could get electronic reversing without having a stupid pile of silicon. But that's about all the more I'm going to say about brushed motors. They are interesting beasts. They are very, very much a pure mechanical solution, and they can work very well. They do have a wear item that needs to be that you need to be aware of. There is brushes that are riding on a commutator, and those need to be checked at some frequency to make sure they aren't worn out. But now we're going to move on and talk about brushless motors. Again, in the theme of how cheap is silicon, to drive a brushless motor, you need 6 times the FETs that you need to drive a permanent magnet motor. Because instead of having 1 coil that you always need to drive in the same direction, now you've got 3 coils that you need to drive in either direction. Well, actually, you've got 3 connections that you either want to tie high or tie low or leave floating. Short answer is it takes 6 times the FETs as a brush motor. So again, in ye olden days where silicon was expensive, these didn't happen. And in the modern days where silicon is cheap, you get cheap brushless motor controllers out of China that will drive really ridiculous random things. And so you can actually get a brushless controller with reasonable specs for a reasonable amount of price. Again, the main difference between a brushed and a brushless is what is doing the commutation. In a brushed, you've got a physical thing that is switching polarities. On a brushless, you've got a microcontroller that is saying, I think we should go positive, negative, and then negative, positive. And that's actually sequencing things around. So there's an important note here about sensored versus sensorless. A sensored motor has your coils and has a set of Hall effect sensors that the motor controller just reads, and it assumes that they are timed correctly, and by reading the three Hall effect sensors either are high or low, and that gives you a 3-bit number that gives you 8 states, and you read your state and you do what the state tells you to. And they're actually bone simple in the control logic because it's read 3 digital values, do a thing because of that. And they're really simple to implement. You do have to actually put sensors in a logical spot, because if you don't have your sensors in a logical spot, the thing doesn't work. Again, that's where we go back to timing. If you have them perfectly timed, it will work. If you have them too far out of timing, the thing will just lock to a phase. A sensorless motor controller is kind of interesting because it actually is it's only driving, you've got 3 wires going into the motor. At any one given time, 2 of them are being driven and 1 of them is floating. And so a sensorless motor controller is measuring what the voltage on the floating leg is doing, and based off of what it's doing, that's how it decides that, oh, we should go to the next thing and power these 2 instead of these 2. And so it's kind of cool because you can have fewer wires to run. Timing is less of an issue because you don't have to worry about hysteresis and sensors. It is what it is. Like, the voltage that you're sensing is the voltage that's happening. You can make intelligent decisions about it. The biggest problem with the sensorless is your startup condition. When it's not moving, you don't have any back EMF, and so you don't know what to do. Typically, when you're talking about an electric vehicle, you're talking about a sensor motor controller so that it actually does know what to do. Sensorlesses are very, very common when you're talking about quadcopters because they're simpler. You don't have to have Hall effect sensors. And on a quadcopter, when you're talking about spinning a blade through the air, your startup characteristics is pretty much no load. A slow moving propeller doesn't have very much load on it. A fast moving propeller does have load. And so on those, the sensorless controller can just guess. It just starts energizing some coils and hopes that we start spinning, so that it hopes that it can get going. And that generally works out pretty well for quadcopters. Doesn't always work out so well on traction vehicles. So if you do decide to build a solely electric vehicle that has a sensorless controller, build it on something that you can get moving. So if you've got a kick scooter that you kick a couple of times, you get it rolling, and then start applying power, because then you've got motion, you've got spinning, and you're happy. If it's a bike, push off, pedal a couple of times, and then apply power. Everything kind of works out better that way. Another thing to note here with brushless controller is ERPM, which is electrical RPM. Everybody's pretty familiar with what mechanical RPMs are, how quickly is that shaft spinning. Electrical RPMs is you take how fast is that shaft spinning, multiply it by the number of poles that your motor has, and that's your electrical RPM. That comes into play when you talk about how quickly can I commutate this, because you can get into a situation in which your motor controller can't keep up. Your motor controller is only designed to do a certain number of RPMs, a certain number of commutation cycles a second, and if you multiply your mechanical RPM by your poles, you can get screwed. That really isn't too much of a problem when you're talking about like an e-bike kit, because when you're buying your motor and motor controller together as a kit, someone has already done this matching. If you're doing a la carte things where you buy a motor from this vendor and a motor controller from this vendor, that's just a thing to be aware of, is that you're going to have to calculate your ERPM and make sure that your motor controller can handle that. Another interesting thing that really happens in brushless, especially when you're talking about brushlesses for quadcopters, is the discussion of an in-runner versus an outrunner. And that's really what part is spinning versus what part is stationary. When you traditionally think of a motor, you traditionally think of an in-runner motor, and that you've got a case that's stationary and you've got a thing in the middle that's spinning. Well, quadcopters have realized that you can change your physics a little bit by putting the magnets on the outside and keeping the coils on the inside, stationary coils on the inside, magnets on the outside, and you get an outrunner motor. And that's where you've got you've got legs coming out the bottom that are stationary with your coils attached to them, and then on the top you've got a cap around, and that cap is actually spinning. That isn't too much of a consideration. Just that decision will affect what your KV/KT numbers look like, because of moment arms and where your torque is being generated. But a consideration, because if you have an outrunner motor, the outside of that thing's going to be spinning. Don't
Mount to a vehicle.
Yeah, you got to be a little bit more creative about mounting. You can only mount from one side of it. You can't mount from both sides of it. That means bearings are only on one side. That means you're cantilevering. That means there's some mechanical considerations that happen there. Also, don't dangle wires against the thing because it's spinning and it'll rip your wire out. Another topic when we talk about brushless are alternators. Alternators are silly devices. An alternator is actually basically the brushless equivalent to a SEPEX motor, if you take off their rectifying diode. An alternator in its normal configuration, you have a pair of slip rings that are applying current to rotating coils that are in the middle, and you have a three-phase winding on the outside that's stationary that is going through a rectifying bridge. And what your car does is applies 12 volts to the slip rings. That creates a magnetic field on the inside. That spinning magnetic field generates current on the generates voltage and current on the outside that goes through the rectifier. That starts shoving current into your battery and you're charging. The downside to an alternator is that if you don't have a battery in the first place, it can't actually do anything because it needs current to create the magnetic field to then actually work. But it turns out that if you take your alternator and you rip off that diode rectifier bridge, you've got 3 wires to stationary coils, and you've got a thing that you can apply current to and get a magnetic field, and that looks a hell of a lot like a brushless motor. The interesting nuance between that and a brush motor is because your slip rings are a downside of a brush is that your commutator is switching positive and negative with inductors. I don't like that. But with an alternator, it's not. They're slip rings that are just brushes riding on a thing that stay consistent. And so you actually have significantly less brush wear in an alternator than you do in a brush motor. But if you run a fixed voltage through the slip rings, then you can pretty much just grab a brushless motor controller and hook her up and it'll run, which is kind of a cool thing. It also turns out that the pole pairs in most most alternators are the same amount of pole pairs that happen to be in CD-ROM drives. So you can take a CD-ROM drive, rip the motor out of it, rip the magnet case out of that, glue that to the shaft of the alternator, and then you can sense off of the magnets that have been glued to the shaft rather than sensing on the actual magnets that are inside of it, which is kind of a neat hack, because that means you don't have to actually open up the alternator. You can just glue something to the back shaft. That also is a neat hack because depending on how strong your glue is and whether you're using a friction foot or glue, you can actually time the motor. You can just kind of rotate the magnets a little bit that your hall sensors are timing off of and actually see the effect of timing the motor. Final 2 categories of brushless motors I'm going to really talk about are PMAX and induction motors. PMAC is permanent magnet AC motor, which is actually just big boy speak for a brushless DC motor. So if you look at a traction motor for a car, no one's going to say, I've got a brushless DC motor in my car. No, they're either going to say they've got a PMAC or they've got an induction motor. Why they decided they want a different term, I don't know, but a PMAC is the same thing as a brushless motor. It's just bigger. Again, in the theme of big magnets are expensive, the other alternative is, again, going back to the fact that if you've got a moving coil if you've got a coil moving through a magnetic field, you get current, you can build an induction motor, which is a case that has fixed coils on it, and on the stator, and on the rotor, you've got coils that are just looped back on themselves. And so as you apply current through the stator, induces current in the rotor. That causes the rotor to make a magnetic field, but then the stator is driving against that then causes motion. Again, swapping copper for magnets, because copper is cheaper than magnets. That has some interesting considerations when you start talking about slip angle. When you really start talking about configuration and matching your motor controller to your motor, there are a whole lot of variables that you have to tweak in order to get an induction motor to actually induction properly. If you look at like our table saw in the back room, that's also an induction motor. That one cheats because it's got AC being fed into it. It doesn't have to produce its AC. I mean, all of these brushless motors are really AC motors that you're cheating. You're taking DC and you're creatively switching it and creatively changing polarities, and it kind of acts like AC. But that's a lot to say about different motor types. Generally speaking, if we're just going to broadly generalize here, brushless are higher performance than brush. The electrical commutation that you can do is getting to a state that it is better than what a brush motor can do. But if you got a budget, if you really want some torque on a budget, you find yourself a shunt wound DC motor. That'll get you some torques. And that can get you a whole mess of fun for not a whole lot of motor investment. And again, if you're going with a brushless because you want better efficiency, better control logic, you probably want to have a sensored motor because it handles low RPM operation better than a sensorless. If you can find one, you actually kind of want a hybrid controller. You want a sensored controller that has sensorless capability because you really want to use the sensors at low RPM and the sensorless at high RPM because of how because of the timing issues. Because at high RPM, your sensor hysteresis is going to cause you timing issues. But that's a whole lot to say about motor types. Anybody got questions? No questions.
How can you tell what you have based upon?
So you got a motor sitting there and you're wondering what it is.
Yeah.
Step one, how many wires does it have? If it's got 2 wires, it's probably a brush motor. If it's got 3 wires, it's probably a brushless motor. Within either of those, how can you tell?
I know this is a brush motor.
Yes. So it doesn't especially matter too much what the specific type of brush motors are if you get 2 wires coming out of it, because you apply power and it spins. And if you really want to tell whether you've got a permanent magnet versus a series mount, if you reverse the wires, does it spin the opposite direction? If it spins the opposite direction, then it's a permanent magnet. If it spins the same direction, then it's a series or a shunt mount. Because of double negatives. The other consideration, or the other way that you can kind of tell, is if you take a wrench and you turn, without having anything hooked up, if you turn the motor, a permanent magnet will cog, whereas a induction motor won't as much. And what I mean by cogging is that there's going to be some latent magnetic field in your rotor just because of saturation and hysteresis and stuff. And so on a permanent magnet, when you take your wrench and you turn it, you can feel it jump and pulls. Whereas a series mount, you won't. Another big way to tell is if you spin it at any appreciable RPM. If you short the wires together, does it increase the load? That'll mean that it's acting as a generator. Whereas a series mount motor, you have to apply a magnetic field in order to kind of kickstart that, similar to the discussion about an alternator. With your brushless, how do you tell between a sensored and a sensorless? How many wires do you have? If you got 3 big wires and 5 small wires, you got a sensored motor. If you got 3 big wires, then you got a sensorless. You can kind of tell, hey look, I got sensor wires, or yeah, there are no sensor wires. How do you tell characteristics like how many pole pairs? Really, that's going to require that you break open or the motor and actually look and see where your magnets are and how many magnets are there. Or in the case of an alternator, how many coils are there. And you count the number of magnets and divide by 2 because it's pole pairs, and the number of magnets is how many poles. Or you could just kind of ignore that and hook up a motor controller and see what happens. I mean, that's a very popular option. Just hook up a motor controller and see what happens. I mean, you can science all of this, all that you want. At the end of the day, does it work? Some mechanical consideration here. Motors are rotating. That means that there will be some amount of rotational force that is trying to happen on the case itself. If you've got your motor with a chain drive to a wheel, and your motor's trying to spin the chain to spin the wheel, and the wheel doesn't want to spin because, you know, you're a fat ass sitting on the vehicle, that means that the motor casing is going to try to rotate the opposite way. So you kind of have to consider that when you're building your motor mounts, so that, you know, you can handle the equal and opposite torques that are happening. Motors don't like axial loads. So your motor's sitting there, you got an axle through it. If you're pushing or pulling on that axle, it does not like that. Motors, generally speaking, have straight bearings in them that don't like that, like forces applied to them that will cause misalignment, that will cause badness to ensue. Another consideration when we're talking about these motors here, your magnet gap is probably less than a quarter inch. Like you're not talking about very much room between the spinny bit and the not spinny bit. So don't apply too much mechanical force to cause that to not be the same gap that it's supposed to be. That's kind of bad. So if you are going to be pushing on the motor shaft, make sure that you've got external mechanical setups, so that you have things like thrust bearings, so that you're transferring the load not into the motor but into something else. Another mechanical consideration, throttle should return to 0. If you let go, you should stop applying power. That's generally a good concept here. Not exactly mechanical, but it bears mentioning here. When you let go, things should stop. That's a good idea. Also, not necessarily mechanical, but packaging more than anything. Motor controllers may require heat sinks. Some motor controllers have enough integral heat sinking, and the airflow across the case is fine. Some motor controllers really tell you bolt this thing to a giant chunk of metal because we expect the giant chunk of metal to be a heat sink for us. If you actually rip apart a motor controller and look inside, 9 times out of 10, their FETs are actually bolted, are isolated, but are bolted to the aluminum extrusion of the case, and the case is its heat sinking. Particularly on forklift motor controllers, they also tell you to bolt the case to a heat sink because they're expecting that their FETs are bonded to the backside of the case, and they're expecting that that's bonded, thermally bonded to some giant chunk of metal that can get the heat away. So now we're going to move on to talk about abuse and what happens when you abuse things. First off, I'm going to mention that power ratings really need a time value associated with this. There's a whole lot of difference. This is also similar to cars. You buy a 1,000 horsepower car. How long can you get 1,000 horsepower out of that car engine? About 10 seconds, maybe. Then your engine explodes. You buy a 1,000 maybe not 1,000. You buy a 500 horsepower tractor. How long can you get 500 horsepower out of that? All day long. It has a coolant system designed to run at peak power all day long. So when you're shopping for electrical components, if you can figure out what time their power rating is for, that's important. Kelly motor controllers actually on their spec sheet give you a 15-second burst, 1 minute average, and a 1 hour average. Generally, you don't see anything longer than a 1 hour average, because by the time you've hit 1 hour, everything is heat soaked, and it is steady state. But there's a difference between what can you peak through this, how much can you force through it in 1 instant, versus how long can you actually run this sustained. And that really comes down to the second bullet here, and that heat is the enemy. All of the system abuse that we're talking about is the fact that heat is bad. More power, more voltage causes more current, causes more heat. How do you get the heat away from things? With motors, one important consideration, especially with motors that have permanent magnets, is that magnets have two different temperatures. One temperature at which they start losing magnetic field, and another temperature in which they lose all of their magnetic field. I know the losing all is called their Curie temperature. I forget what the other term is. But for a neodymium magnet, which is a very common magnet to be used, it's 110, 120 degrees Celsius, which is warm but not that warm. Another thing to note is that a motor can be perfectly happy running at a temperature that will burn you. So just because it's too hot, if you can touch the motor and not get burnt, you're not abusing the motor very much. If you can touch the motor and it's uncomfortable, you might be abusing the motor. So feeling it isn't exactly a very good indication. That, again, going back to types of motors, that's where series wound motors are more fun than permanent magnet motors, because copper melts at a pretty darn high temperature. Solder melts at a pretty darn high temperature. You can abuse the shit out of a series wound motor before you start running into permanent damage.
I know RC car motors can get hot enough to melt the solder off the motor connector.
Oh yeah. No, so at that point, the magnets are probably being damaged. They're actually almost certainly the magnets are being damaged because of overheating. But if it was a series wound, that'd be fine. You can abuse a motor to the point that you're starting to debrace your connections. That's kind of bad. You should avoid that, generally speaking, but you don't permanently harm them. So the other mention of system abuse here is overvoltage. So I've got a 12-volt motor. I want more power out of it. What if I apply more voltage? Well, step one, don't do that to your motor controller. If you've got a 12-volt motor controller, give it 12 volts. If you want to have a system running at a higher voltage, get a different motor controller. Motor controllers will explode if you put more voltage than they want. Straight up, they explode. But what happens to the motor? Say you get a different motor controller and you apply higher voltage to it. Well, it spins faster with no load on it, because your KV number. That could be a problem because it could spin itself to death. If it's unbalanced, it might fly apart. But assuming that you're loading it, that's okay. It'll have more torque because, again, going back to our simplified model, you've got more voltage across the same amount of resistance. You get more torque. The more torque and more current also means it heats up faster. So as long as you can get the heat away from it, you can overvoltage a motor. Again, up to a point. At some point, if you way overvoltage your motor, you're going to start arcing internally. The windings that are wound there have an insulation around them, and that does break down at a certain voltage. Fortunately, that voltage is about 300 usually. It'd actually be rather annoying for a manufacturer to get magnet wire that has less than a 300 volt insulation on it, just because it's like, why? We aren't going to special make magnet wire that has less insulation than that. And if you got a 300 volt insulation, you can be a thing that plugs into a wall. So that's kind of, you probably don't have to worry about that fact, which is why I didn't put a bullet up here. The other consideration when you're talking about abuse is iron saturation. So again, going back to particularly more on your series DC, on your series DC and on your alternators, at some point the things that they are coiled around can only have so much magnetic field in them. And you apply more current, you don't get any more magnetic field, you just get more heat. There's a physical limit to the amount of magnetic flux coming out of that iron. And so you're going to saturate. So at some point when you're abusing the crap out of a thing, you start really hitting diminishing returns. Maybe it just doesn't help anymore. So that is a thing alternator's rotor field, that saturation happens at about 12 volts. Coincidentally, what a car battery voltage is. It's almost like they designed it for that or something. It's weird. It's weird how those things happen. So if you're going to build something with an alternator motor, make sure you have a way of powering the rotor with 12 volts. Don't apply full pack voltage, because you're just going to overheat it and not get anywhere. So that's really all the more that I have to say about motors and motor controllers. Anybody, again, have any questions? Thoughts, theories, concerns? One other thing that I had in my draft that I didn't actually have a bullet in here for, gearing. Again, going back to the interplay between KT and KV, and whether you've got a fast torquey or slow and torquey or fast and low torque. You can also solve that problem mechanically with gears. Gears trade RPMs for torques, similarly to how your motor winding setup also trades those two things off. So if you've got a motor and it doesn't spin in the RPM range that you want it to, you can mechanically solve that problem. And batteries. One thing to note here, I'm only going to be talking about lithium type batteries. I'm not going to be bothering with leads or nickel metal hydrides or nickel cadmiums because they're crap. Lithiums significantly outperform all of the other chemistries, and so I don't really feel like wasting time talking about the other chemistries. You're probably not going to be talking about enough battery that the price differential between a lithium and a lead is going to be that significant. So go with lithiums, they're better. Some terminology here. A cell, like in biology, is the smallest indivisible unit. A battery is a two-terminal device that is a collection of cells. Technically, a AA battery is a bit of a misnomer. It is more technically correct to call it a AA cell. You can have single-cell batteries. That is possible. A collection can be a collection of one, but technically, a AA is a single cell. A 9-volt battery is actually a battery. A 9-volt battery is a collection of 1.5-volt cells. They're either weird little pouches or they're quad A's. But a 9-volt is properly a battery because it is a collection of cells. A car battery, a 12-volt lead acid, is also actually a battery because it's a collection of 6 2-volt lead cells. Other terms that are important here is that series and parallel connections. Series is when you connect plus to minus and stack them on top of each other. That increases your voltage but not your current. Taking two cells and putting them together in some way at all always increases your total energy capacity because now you've got more cells. But whether you do that by stacking them in series to increase voltage, or whether you stack them in parallel, plus to plus, minus to minus, to increase current capacity, but not voltage. So again, getting more cells together always results in more energy. It's just, does that energy come through higher voltage or higher current? The other consideration here, just because I'm talking about series and parallel, you always want to connect your cells in parallel first, and then connect those parallel blobs in series. It helps a whole lot with battery management and not exploding your cells to do it that way. I can get into a lot of nuances and details, but if you want to do that.
Along those lines, I've always found it weird to put a lot of batteries in series because I feel like at some point the amount of voltage that you're putting into the next battery is then adding more voltage to that. In my head, it seems like eventually that would be a problem.
Well, eventually it is a problem.
Okay.
But it depends on what kind of problem you're talking about.
Yeah.
So problems that you can cause from having too much voltages. They're, strictly speaking, stacking cells on top of each other, you're gonna run out of time and patience in cells before you really have problems with, oh god, I have too much voltage. Like, too much voltage really is when you're talking about kilovolts. Like, that's when you start arcing, like, yeah, it takes kilovolts to have arcs. Now, too much voltage in terms of killing you, depends on who you ask. Most standard bodies say 48 volts is the threshold between safe and not safe. Technically, you can kill yourself with a lot less than 48 volts, but it just becomes a lot easier to greater than 48 volts. Again, with the physical considerations that you have of a motor and what voltage you want to run the motor at, that's really what determines what voltage you want, more than anything else. You're not going to run into issues that you're going to have to find. Stacking cells, you're not going to run into issues that you're going to have higher voltage than what the insulation rating on your wire is. Just, again, it's easy enough to get a couple hundred volts of insulation rating on a wire, and it's hard to find a wire that can't handle that.
But it's not really an issue, so let's just as a fun thought experiment. We were gonna stack AA batteries in there, AA cells. The batteries themselves don't really care
No.
how much voltage is running through.
Nope. So voltage isn't a cross measurement, current is a through measurement, and so the battery actually, voltage is also all relative. Like when you talk about electronics, you draw a circuit up and you draw a ground. Where you draw a ground doesn't actually matter in terms of it being a circuit. Nobody cares, a cell doesn't care that it's stacked on one other or 100 others in terms of how it behaves as a cell. Now, you might care that I've got 100 cells stacked together, 100 times 1.5 gives me 150 volts from tip to tip on that battery. That might care and might scare you because 150 volts of DC through a battery without a fuse can do some damage.
Sure. But the batteries themselves don't care.
Nope, that doesn't matter to them.
Okay.
Now, a thing to note, I think it's, yeah, I've got this on the next slide. I'll get to some more details on my next slide. One other bit of terminology that you might see thrown around is BMS, that is a battery management system. What they do depends on what you actually want them to do, but I'll get into actually what their function is later. But just if you see BMS, I'm talking about battery management system. Short answer is it's a circuit board with some electronically bits on there that is measuring the health of the individual cells that make up the battery. What it's doing about that, we'll talk about later. But at the end of the day, does it work? Some mechanical consideration here. Motors are rotating. That means that there will be some amount of rotational force that is trying to happen on the case itself. If you've got your motor with a chain drive to a wheel, and your motor's trying to spin the chain to spin the wheel, and the wheel doesn't want to spin because you're a fat ass sitting on the vehicle, that means that the motor casing is going to try to rotate the opposite way. So you kind of have to consider that when you're building your motor mounts, so that you can handle the equal and opposite torques that are happening. Motors don't like axial loads. So your motor's sitting there, you got an axle through it. If you're pushing or pulling on that axle, it does not like that. Motors, generally speaking, have straight bearings in them that don't like forces applied to them that will cause misalignment, that will cause badness to ensue. Another consideration when we're talking about these motors here, your magnet gap is probably less than a quarter inch. Like you're not talking about very much room between the spinny bit and the not spinny bit. So don't apply too much mechanical force to cause that to not be the same gap that it's supposed to be. That's kind of bad. So if you are going to be pushing on the motor shaft, make sure that you've got external mechanical setups so that you have things like thrust bearings, so that you're transferring the load not into the motor but into something else. Another mechanical consideration, throttle should return to 0. If you let go, you should stop applying power. That's generally a good concept here. Not exactly mechanical, but it bears mentioning here. When you let go, things should stop. That's a good idea. Also, not necessarily mechanical, but packaging more than anything. Motor controllers may require heat sinks. Some motor controllers have enough integral heat sinking and the airflow across the case is fine. Some motor controllers really tell you bolt this thing to a giant chunk of metal because we expect the giant chunk of metal to be a heat sink for us. If you actually rip apart a motor controller and look inside, 9 times out of 10, their FETs are actually bolted, are isolated, but are bolted to the aluminum extrusion of the case, and the case is its heat sinking. Particularly on forklift motor controllers, they also tell you to bolt the case to a heat sink because they're expecting their FETs are bonded to the backside of the case, and they're expecting that that's bonded, thermally bonded to some giant chunk of metal that can get the heat away. So now we're going to move on to talk about abuse and what happens when you abuse things. First off, I'm going to mention that power ratings really need a time value associated with them. There's a whole lot of difference. This is also similar to cars. You buy a 1,000 horsepower car. How long can you get 1,000 horsepower out of that car engine? About 10 seconds, maybe. Then your engine explodes. You buy a 1,000 maybe not 1,000. You buy a 500 horsepower tractor. How long can you get 500 horsepower out of that? All day long. It has a coolant system designed to run at peak power all day long. So when you're shopping for electrical components, if you can figure out what time their power rating is for, that's important. Kelly motor controllers actually on their spec sheet give you a 15-second burst, 1 minute average, and a 1 hour average. Generally, you don't see anything longer than a 1 hour average because by the time you've hit 1 hour, everything is heat soaked and it is steady state. But there's a difference between what can you peak through this, how much can you force through it in 1 instant versus how long can you actually run this sustained. And that really comes down to the second bullet here, and that heat is the enemy. All of the system abuse that we're talking about is the fact that heat is bad. More power, more voltage causes more current, causes more heat. How do you get the heat away from things? With motors, one important consideration, especially with motors that have permanent magnets, is that magnets have 2 different temperatures. One temperature at which they start losing magnetic field, and another temperature in which they lose all of their magnetic field. I know the losing all is called their Curie temperature. I forget what the other term is. But for a neodymium magnet, which is a very common magnet to be used, it's 110, 120 degrees Celsius, which is warm, but not that warm. Another thing to note is that a motor can be perfectly happy running at a temperature that will burn you. So just because it's too hot, if you can touch the motor and not get burnt, you're not abusing the motor very much. If you can touch the motor and it's uncomfortable, you might be abusing the motor. So feeling it isn't exactly a very good indication. That again, going back to types of motors, that's where series wound motors are more fun than permanent magnet motors, because copper melts at a pretty darn high temperature. Solder melts at a pretty darn high temperature. You can abuse the shit out of a series wound motor before you start running into permanent damage.
I know RC car motors can get hot enough to melt the solder off the motor connector.
Oh yeah. No, so at that point, the magnets are probably being damaged. They're actually almost certainly the magnets are being damaged because of overheating. But if it was a series wound, that'd be fine. You can abuse a motor to the point that you're starting to debrace your connections. That's kind of bad. You should avoid that, generally speaking, but you don't permanently harm them. So the other mention of system abuse here is overvoltage. So I've got a 12 volt motor. I want more power out of it. What if I apply more voltage? Well, step one, don't do that to your motor controller. If you've got a 12-volt motor controller, give it 12 volts. If you want to have a system running at a higher voltage, get a different motor controller. Motor controllers will explode if you put more voltage than they want. Straight up, they explode. But what happens to the motor? Say you get a different motor controller and you apply higher voltage to it. Well, it spins faster with no load on it because your KV number. That could be a problem because it could spin itself to death. If it's unbalanced, it might fly apart. But assuming that you're loading it, that's okay. It'll have more torque because, again, going back to our simplified model, you've got more voltage across the same amount of resistance. You get more torque. The more torque and more current also means it heats up faster. So as long as you can get the heat away from it, you can overvoltage a motor. Again, up to a point. At some point, if you way overvoltage your motor, you're going to start arcing internally. The windings that are wound there have an insulation around them, and that does break down at a certain voltage. Fortunately, that voltage is about 300 usually. It'd actually be rather annoying for a manufacturer to get magnet wire that has less than a 300 volt insulation on it, just because it's like, why? We aren't going to special make magnet wire that has less insulation than that. And if you got a 300 volt insulation, you can be a thing that plugs into a wall. So that's you probably don't have to worry about that fact, which is why I didn't put a bullet up here. The other consideration when you're talking about abuse is iron saturation. So again, going back to particularly more on your series DC, on your series DC and on your alternators, at some point the things that they are coiled around can only have so much magnetic field in them. And you apply more current, you don't get any more magnetic field, you just get more heat. There's a physical limit to the amount of magnetic flux coming out of that iron. And so you're going to saturate. So at some point when you're abusing the crap out of a thing, you start really hitting diminishing returns. It just doesn't help anymore. So that is a thing to be aware of, not especially important. One major key to note on that is actually that saturation on an alternator. On an alternator's rotor field, that saturation happens at about 12 volts. Coincidentally, what a car battery voltage is. It's almost like they designed it for that or something. It's weird. It's weird how those things happen. So if you're going to build something with an alternator motor, make sure you have a way of powering the rotor with 12 volts. Don't apply full pack voltage. You're just going to overheat it and not get anywhere. So that's really all the more that I have to say about motors and motor controllers. Anybody, again, have any questions? Thoughts, theories, concerns? One other thing that I had in my draft that I didn't actually have a bullet in here for, gearing. Again, going back to the interplay between KT and KV, and whether you've got a fast torquey slow and torquey, or fast and low torque. You can also solve that problem mechanically with gears. Gears trade RPMs for torques, similarly to how your motor winding setup also trades those two things off. So if you've got a motor and it doesn't spin in the RPM range that you want it to, you can mechanically solve that problem. And batteries. One thing to note here, I'm only going to be talking about lithium type batteries. I'm not going to be bothering with leads or nickel metal hydrides or nickel cadmiums because they're crap. Lithiums significantly outperform all of the other chemistries, and so I don't really feel like wasting time talking about the other chemistries. You're probably not going to be talking about enough battery that the price differential between a lithium and a lead is going to be that significant. So go with lithiums, they're better. Some terminology here. A cell, like in biology, is the smallest indivisible unit. A battery is a two-terminal device that is a collection of cells. Technically, a AA battery is a bit of a misnomer. It is more technically correct to call it a AA cell. You can have single cell batteries, I mean, that is possible. A collection can be a collection of one, but technically a AA is a single cell. A 9-volt battery is actually a battery. A 9-volt battery is a collection of 1.5-volt cells. They're either weird little pouches or they're quad A's. But a 9-volt is properly a battery because it is a collection of cells. A car battery, a 12-volt lead acid, is also actually a battery because it's a collection of 6 2-volt lead cells. Other terms that are important here is that series and parallel connections. Series is when you connect plus to minus and stack them on top of each other. That increases your voltage but not your current. Taking two cells and putting them together in some way at all always increases your total energy capacity because now you've got more cells. But whether you do that by stacking them in series to increase voltage, or whether you stack them in parallel, plus to plus, minus to minus, to increase current capacity, but not voltage. So again, getting more cells together always results in more energy. It's just, does that energy come through higher voltage or higher current? The other consideration here, just because I'm talking about series and parallel, you always want to connect your cells in parallel first, and then connect those parallel blobs in series. It helps a whole lot with battery management and not exploding your cells to do it that way. I can get into a lot of nuances and details, but if you want to do that.
Along those lines, I've always found it weird to put a lot of batteries in series because I feel like at some point the amount of voltage that you're putting into the next battery is then adding more voltage to that. In my head, it seems like eventually that would be a problem.
Well, eventually it is a problem.
Okay.
But it depends on what kind of problem you're talking about.
Yeah.
So problems that you can cause from having too much voltages. They're, strictly speaking, stacking cells on top of each other. You're going to run out of time and patience in cells before you really have problems with, oh god, I have too much voltage. Like, too much voltage really is when you're talking about kilovolts. Like, that's when you start arcing. Like, it takes kilovolts to have arc. Now, too much voltage in terms of killing you, depends on who you ask. Most standard bodies say 48 volts is the threshold between safe and not safe. Technically, you can kill yourself with a lot less than 48 volts, but it just becomes a lot easier to greater than 48 volts. Again, with the physical considerations that you have of a motor and what voltage you want to run the motor at, that's really what determines what voltage you want, more than anything else. You're not going to run into issues that you're going to have to find. Stacking cells, you're not going to run into issues that you're going to have higher voltage than what the insulation rating on your wire is. Just, again, it's easy enough to get a couple hundred volts of insulation rating on a wire, and it's hard to find wire that can't handle that.
But it's not really an issue, so let's just as a fun thought experiment. We were gonna stack AA batteries into AA cells. The batteries themselves don't really care
No.
how much voltage is running through.
Nope. So voltage isn't a cross measurement, current is a through measurement, and so the battery actually, voltage is also all relative. Like when you talk about electronics, you draw a circuit up and you draw ground. Where you draw ground doesn't actually matter in terms of it being a circuit. Nobody cares, a cell doesn't care that it's stacked on one other or 100 others in terms of how it behaves as a cell. Now, you might care that I've got 100 cells stacked together, 100 times 1.5 gives me 150 volts from tip to tip on get to it. I'll get to some more details on my next slide. One other bit of terminology that you might see thrown around is BMS. That is a battery management system. What they do depends on what you actually want them to do, but I'll get into actually what their function is later. But just if you see BMS, I'm talking about battery management system. Short answer is it's a circuit board with some electronically bits on there that is measuring the health of the individual cells that make up the battery. What it's doing about that, we'll talk about later. Overall heating of the system. Right where the weld is, yeah, it gets hot, but the majority of the cell doesn't. So prefer to weld your packs together rather than solder them. You're less likely to anger your cells. Some cell parameters that we talk about that I've alluded to a little bit. Voltage is purely a function of chemistry. A given chemistry will have a given cell voltage. A lead acid cell is 2 volts. A alkaline cell is 1.5 volts. A nickel cadmium cell is 1.2 volts. A lithium cell is 3.7 volts. A lithium iron cell is 3.2 volts. Fundamental to the chemistry. And that's where you find your number for your divisor when you're trying to figure out how many S's you need. Is you take your chemistry, that gives you a voltage.
Is there a table for the lithium?
Short answer is lithiums are 3.7. If it's any, the only exception to that is a lithium iron. When I talk about lithiums, I'm actually talking about a half dozen specific chemistries that are kind of 3.7. 3.7. Don't worry about it.
Yeah. Well, I knew there was a 3.7 and 3.2
Yep.
from what you guys had said before. That's why I was wondering. You started talking chemistry.
Nope.
It must be a range.
No. Most lithiums are 3.7. The outlier is a lithium iron. The real thing this is actually caused by is the amount of chemistry that's happening in the reactivity. The higher reactivity causes higher voltage.
Is that the amount of lithium?
No,
Oh.
no, it's a whole mess of chemistry that I don't know because I'm not a chemist. There's a whole. Batteries are a very, very interesting intersection of chemistry and electronics, and that they're kind of passive, kind of chemical reaction, kind of this, kind of that, weird things. I know lead acid batteries behave significantly differently if you are slowly discharging versus quickly discharging, because a slow discharge will end up slow discharge is a much more of a slower chemical reaction, but there's a faster chemical reaction that can happen. There's actual chemistry, serious chemistry happening in your lead acid battery when you're charging and discharging. A lithium is actually a whole lot more like a capacitor when it's charging and discharging. It's weird. Chemistry, physics. Capacity is determined primarily by size. The physically larger the cell is, the more capacity that it has. So you can get, again, the difference between a 18650 and a 25 whatever. The 25 whatever is physically larger, so will have larger capacity. Both will be 3.7 volts, but one will have a larger capacity. It's actually, capacity is a function of surface area of plates. So internally in your battery, you got a whole bunch of pluses and a whole bunch of minuses that are all stacked together and wired in parallel internally. And the more of them that you have, or the more area that you have there, the more capacity that you have. So consequently, the bigger the cell, the more you've got. The discharge rate is determined by the specific subset of chemistry that you have. You can optimize for kind of a few different variables. You can optimize for capacity in a given volume. You can optimize for a discharge rate in a given volume. Those are going to be called either your energy density or your power density. Energy density is capacity, power is instantaneous. set of chemistry you put into that cell. Short answer is you'll get a cell, it'll have a C rating on it, and don't abuse the C rating too much. Again, going back to earlier discussions, C ratings also need to have a time associated with them, because what you can instantaneously pull out of a cell is different than what you can pull out of a cell for the long haul. The C rating, I keep mentioning C. I'll actually tell you what I mean by C here. C is capacity. So if you have a 1 amp hour cell and it's got a 5C, it's rated for a 5C discharge, that means you can pull 5 amps out of it. 1 amp hour times, 1 times 5 is 5. If it's rated for a 10C, you can pull 10 amps out of it. If it's rated for a 100C, you can pull 100 amps out of it. It's going to be a hell of a discharge on that little tiny 1 amp hour cell, but if they say it can do it, it can do it. On the flip side, you also see C ratings for charging. Usually less of a problem, because usually when you're talking about, well, for small EVs like bikes, it'd be relatively easy to hit a multiple C on their charge. If I've got a 1.5 amp hour pack, a 2C charge is only 3 amps. I can usually find a 48 volt 3 amp charger. That wouldn't be that hard to do. But if you're talking about, say, a Tesla that has an 80 kilowatt hour battery pack, if I wanted to do a 5C charge on an 80 kilowatt pack, that means I need 80 times 5, I need 400 kilowatts to charge that. 400 kilowatts means I'm going to have a fat ass wire going into that. That's not very likely that you're going to do a 5C charge on a Tesla.
You mean you're parked next to a power reservoir?
Yeah, you're parked next to a substation to pull 500 kilowatts. Somebody will notice if you're doing that. So that's actually why when you see things, that's actually why charging C rates are significantly less important than discharging C rates. Because when you get into any battery of any significance, you can't get a power cord large enough. Like, it's just not feasible. So you just don't care as much. That's also why, coincidentally, most fast charging for cars is a 20-minute charge. It's a C/3. Every cell ever that's been produced in the last 10 years practically can handle a C/3 or a 3C charge. I won't complain too much about it. Other consequence of the fact that we're talking about C ratings here is that the larger the capacity, the larger the C is, so the larger the multiplication is. So a 5 amp hour pack can naturally instantaneously discharge more, can discharge faster than a 1 amp hour pack. If I've got 5C rated cells in my 1 amp hour pack, I can pull 5 amps. If I've got 5C rated cells in my 5 amp hour pack, I can pull 25 amps. So a solution to hit the instantaneous rating that you need for your motor controller is build a bigger battery pack. You can either get more expensive cells that have a faster instantaneous discharge, or you can just put more of them on there. And if you wanted the range anyway, put more of them on there. It really only matters when you're talking about things like power tools. The power tools are going to have a pretty high instantaneous draw and may not actually want to be lugging around that big of a pack. So that's where you start really finding people optimizing for discharge. The other is things that fly. With limited lift capacities, quadcopters are looking for high C-rated cells to go in there because they really care about carrying the minimum amount of capacity to be able to generate the power for their lift. Also, if you happen to talk to electric drag racers, they care about high C-rate cells. Naturally, they want to move their car down that drag strip. So if you really do want to build something that has a high C-rate for discharge and is actually a reasonable cell, I do have a business card of a guy that will sell you battery packs by the horsepower. He actually sells them by their electric horsepower, which is their instantaneous discharge rate. It's also a drag racer, so he cares. They get you a couple thousand horsepower. It's fine.
How much per?
They'll charge a pretty penny for it. So,
Pay some.
yeah. Balancing. I alluded to this previously, but you want to balance your cells because, like I said, if you discharge an empty cell, it's bad. If you
charge a full cell. It is bad. The easiest way to measure things is by voltage. You can't really measure capacity. You can't really tell what their state of charge is, aside from measuring their voltage and guessing. So you would like to have a pack of all of the cells that are identical, because if they're all identical, they all get full the same, they all empty the same, assuming you don't have parasitic loads. There are two major techniques to balancing. There are passive techniques and there are active techniques, and that really means, do I do this once my pack is a thing, or do I do this as a construction of my pack? There are also two major theories that you can get into. There's bottom balancing and there's top balancing. Bottom balancing is where you discharge everybody to the same empty, because you can reliably measure empty, and then you put them all in series, and then you charge them all together until one of them gets full, and then you stop charging. You say, I am full, I am done. And what that does is, if you are driving your pack until it is empty, they will all empty the same, and you will stop, and you won't blow up your pack. If you've got a $12,000 pack in an electric vehicle, you kind of don't want to replace your $12,000 pack. So you'd rather be stranded and have to call somebody to give you a ride than replace your $12,000 pack. And quite a few Ubers, that's the cost of replacing the pack. That does sacrifice capacity, because you have emptied them all. You may have cells that are actually 110 amp hours rather than 100 amp hour, but I've only filled it to the 100 amp hour, and I've left capacity on the table. That's fine, because I don't want to blow up my pack. The other side of the thing is top balancing. Top balancing is usually done at charge time, and what that is you got your BMS sitting there monitoring the individual cell voltages. It's getting current shoved into the whole pack, through the whole pack via the charger at a constant rate, and then it says, oh, that cell's full and that one's not. So I'm going to actually put a resistor in parallel with that cell so I can bleed off some of that current. So rather than having current go into the full cell, it's going to go around the full cell.
How does it know what's in each one?
It has sense leads connected to each of the cells. It has your BMS will have, for a 12-ounce pack, will have 12 lines running to 13 lines ground. It'll have the bottommost, and then it'll have one between every cell, and then it will have 3 other wires. It will have a wire for positive, and that positive goes to both the charger and to your motor controller. Then it will have 2 other wires, one for charger and one for the negative of your motor controller.
You build this in when you get to
You build that into the pack. You weld together your pack, you solder on these tap wires, you connect it to that, you wrap the whole shebang up and say, I have a battery pack. It has 2 terminals. Is there a BMS in there? Shh, don't worry about it, not your problem. Because it's a pack, it has 2 wires. You only ever pull out the 2 wires. The other alternative to that is actually what hobby RC guys do, in that they weld on all of those wires and they just stick them out. And so they've got 3 things coming out of their pack. They've got a fat plus wire, a fat minus wire, and then a balance connector. And when they charge their packs, they plug the 2 fat wires into the charger, and they plug balance into the charger, and all of the logic of that is being done by the balance charger. So they don't fly with the BMS. The BMS is part of their charger, which is fine. It's a perfectly acceptable alternative. If you're building a traction pack, you probably are going to put balancing in. If you're going to put balancing in it, you're going to put it in the pack, and then it's going to take care of everything. You plug a charger in, and the pack is actually what's in control of the charging. The pack really is presenting a load to the charger, and then when it decides it's done, it disconnects. Okay, maybe we have room. Alright, so after I've decided my motor, that's going to establish some key characteristics, like what voltage I want to actually run the thing at. That'll find me a motor controller, and that motor controller will have a current rating. So all of this goes into, I know how much voltage I need, because it's my motor controller. I know how much peak current I want, because again, my motor controller combo. Those 2 numbers, I take the voltage, I divide by 3.7, I figure out what that is. It'll probably be a fractional number. I round,
I either round up or down depending on how ballsy I am, but I round one way or the other. And then I take that number and I multiply it by 4.2 to see what my absolute peak is, because the lithium, again going back to the chemistry, a lithium cell fully charged is 4.2. So I take my 13, say we're talking about a 48 volt e-bike. I divided, it gave me 12 point something or other. 4.2 times 13 gives me a number. I make sure that that number is a smaller number than what my motor controller says for its peak voltage. Because if that number were bigger than what my motor controller said for its peak voltage, I'd blow up my motor controller. I don't want to do that, so I'd have to round down instead of rounding up. So I ascertain that. For funsies, I take that number and I multiply it by 3.4. And that gives me my low voltage cutoff, just kind of as a ballpark of what empty is going to be. And I look at my motor controller and I make sure that it is going to low voltage cut off at the appropriate time. So that then just firms up that, yeah, I really want to build a 13S pack. Alright, now that I want to build a 13S pack, now I need to decide how far do I want to go, how long do I want to go, how much do I actually want to care about this thing. And I was trying to find the number, because there is a number of how many watt hours it takes to move a pound a mile. And I unfortunately could not find that number, but I want to say, it's in the neighborhood of 10 watt hours? I don't know. But there's a number of watt hours to move a pound a mile. And I would use that to figure out how many pounds I want to move, how many miles, and that would give me a capacity. And then I would say, okay, I need 13S, and then I need to figure out the most economical way to get me my capacity. Say I decided that I wanted a 10 amp hour pack, approximately 10 amp hour pack. I would then start going out to various vendors, and I would start seeing what they have available for cells. I would start seeing what options I have, how many in parallel do I need to do, and I'd pick a few candidate cells. Say I find a 2.5 amp hour that's good for a 5C discharge, and a 3 amp hour that's good for a 4C discharge. And so, okay, I want to build a 10 amp hour pack. So that would be four of the 2.5 amp hours. So it'd give me a 13S 4P pack.
That's 13S
times 4. Yep. 56.
52.
Right, 52. Yep.
Yeah,
I was thinking 14.
That's
yep.
the number that
Yep.
brings up all
So-
the time now is 52.
So 52. That'd be how many cells I have to do. I'm not ready to buy them yet,
Yeah.
because I say, okay, now I get a 10 amp hour pack that's good for a 5C discharge. That'll give me 50 amps of instantaneous current if I'm playing within their numbers. Is 50 amps good enough for my motor controller combo? Or is that more than I wanted to put into my motor controller combo? If it's more than I wanted to put in there, I either have to say I need to find a higher C rated cell, or I need to build a bigger pack. One of the two. But I just kind of iterate on that until I figure out I need this many S pack, and here's how many P I want. Then I would go and I would acquire myself a BMS that, depending on how ballsy I really feel like, whether I actually want my BMS to take care of low voltage cutoff or not, I would either buy the cheapest BMS that runs the S count that I want, or I would find a BMS that's rated for the current that I want. The real delineation is, do I want the BMS to actually kill the thing when I'm out, or do I want to just rely on myself? And that's just a pricing difference. It affects how I wire the thing up, but it's a pricing difference. But then I decide on that. I buy one. I order a pile of cells. I order the BMS, and then I go in the back with the welder and I weld my cells into parallel modules, probably with the assistance of the CNC router to route me out a nice 18 millimeter wide channel that has a
3D
or 3D print, or well, I want a jig for welding. I want a thing that I can set a bunch of cells into, that I can set tab strip across and I can just weld, or I can flip over and I can weld. And that gives me my parallel modules. Onto each of the parallel modules, I will solder a balance lead to go back to the BMS. And once I've got all my parallel modules done, I will start then stacking them in series until I get my series done. And then I will weld on a extra tab that I'll probably weld on an extra tab that has a wire soldered to it that then is my pack plus, and do another for my pack minus. Wire in the main pack lines to the BMS and wrap the whole shebang in electrical tape. Probably electrical taping across the terminals before I smash the BMS on top of there so I don't short things out. But then wrap the whole thing in electrical tape and then find some kind of mechanical way to put over that. Fence post happens to be the right approximate diameter to hold a 4P 18650. So you take a hollow plastic fence post, cut it in half, and then shell it over there, and then wrap the whole thing again in some more tape, and call that good. So that'd be how I would construct a pack. Is that enough detail, too much detail? 2/3?
No, it just gives me questions, but I'll do it that way.
Okay, but that's kind of the general thing. And it makes a whole lot more sense when you actually have a project that you actually want to do, that you actually step through all of these things rather than being hypothetical, and that also involves some spreadsheeting, because you can make a whole lot of these decisions a lot better if you've got a spreadsheet in front of you.
And there are websites that will sell you all those bits individually.
Oh, yeah.
pieces
Yeah.
together.
Oh,
Yeah,
God,
yeah.
yes.
You also have options. You also have other lazy options, like going to Lowe's and buying Cobalt tool batteries because they're relatively cheap. Because unlike the other tool brands, they seem to not want to gouge you on battery prices. So you can buy those and just use them straight up, and they've got a BMS on them, and you just don't worry about it. You're like, great, that's fun. I got a charger that I also bought from Lowe's, and it knows how to charge the thing, and I don't have to worry about it. Excellent. You can go to places like Hobby King and buy pre-made packs for hobby RC vehicles. Although the challenge with doing that is you're probably going to pay more because you're buying a fairly niche thing, and you're also probably not going to get exactly what you want because most of those hobby packs are probably going to be higher C rated. You're going to have to parallel things to get enough capacity for what you want, and by that point you don't actually need the C rating. And so you could do that, but it may not be optimal. Maybe good enough if you're just hacking it together for the hell of it.
Is it better to, so I've got a 36 volt motor here. Is it better to get 3 12-volt batteries or try to find an actual 36 volt battery?
It depends on what chemistry you're rolling with. If you're going to go with lead acid, then you would get 3 12-volt batteries and put them in series. If you're going with lithiums, then you're really going to you're probably going to just buy a pack that is to the S number that you want. Yeah. Yeah. You just buy a 10S pack. You call it good. You could buy 2 5S packs and series them, but it's probably going to be a hell of a lot easier to just buy a 10S pack and say, I've got a 10S system.
One BMS instead of 2.
Yeah, that's a better plan overall. Can you get away with not doing that? Yeah. I mean, I'm running my e-bike off of a pair of 6S packs from Lowe's because it was cheaper. And that was for the hell of a project because it was cheaper. So ultimately I do want to build a custom 13S pack for it, but I don't know, I just want to see how cheaply I can hack something together. So third category, safety, maybe, kind of, probably, somewhat. General safety, fuses are good. Fuses protect wires, not electronics. So proper motor controllers do actual current feedback loops and will not light themselves on fire. Sketchy motor controllers are rated for some current they probably won't catch fire on, but if you stall the motor out, they probably will catch fire. Fuses probably won't protect the electronics, but probably will protect the wire. So the gauge of wire that you use has an appropriate fuse for it. Use that so that if you short out your wire, the fuse reliably pops rather than your wire melting and catching fire. Fuses are good. Kill switches can also be good. It's usually a good idea to be able to turn off the thing. Contactors are also good. What I mean by a contactor is a big ass funky relay that is rated for breaking a DC current of what you expect to have. DC currents are a pain in the ass to break because DC likes to arc a hell of a lot more than AC. Because AC you have zero crossings, which snub your arcs. Contactors have magnets in them because magnets can be used to push an arc, and you can actually push the arc to make it longer, which will make it more likely to break. Get a contactor. They're good. Also, contactors, unlike relays, are polarized. Make sure that you have wired your contactor up correctly so that the magnet pushes the arc away, not in. Because if you shouldn't ever need to switch your contactor when you've got current flowing. But if you do, man, you got issues and you really want it to actually turn off. If you really want to be serious about having some kind of kill switch, you can always have a loop back of an extra connector that just has a connector that has a loop on it, and you can have a pull cord on that. And if you really want the thing to be dead, you pull that pull cord, and now you've broken the wire. And assuming that your connector is sufficiently rated and doesn't just melt and weld itself together, that you will probably be breaking the thing. You probably will be okay. But be aware that, there could be a situation in which, especially with a brushless DC motor, you're not likely to have runaway, because if a FET fails, the controller just won't be able to do anything. It won't work. If you've got a brushed DC motor, if things fail in a short condition, that motor's going. It doesn't need any external stimuli. It's got power being applied to it. It's spinning. So you really would like to have something that you can use to shut that off. But like an e-bike, less concerned, because if one of the phases of the motor controller shits itself, that's just not spinning. It can't spin unless something is coordinating the switching action. I'll mention it again. A return to zero throttle is a good idea. You let go of the throttle and it stops applying power, that's generally a good thing. Like if you've, fallen off of the vehicle, it's generally a good thing, but it doesn't keep accelerating. I don't know. Some governing bodies think that that's a good plan. Some governing bodies also test that that's a thing. To make sure you've got springs on throttles and such. Other general safety point to note that if you come from an automotive world, that you should not do is do not ground the frame. In a car, you've got your chassis grounded to your 12-volt system, which is very convenient and very nice for the manufacturer because they don't have to run ground wires around. Do not do that on an electric vehicle because you've got a battery pack that can do some really bad things if it's shorted out. And so you really want to think about single faults. What happens if one of my wires wears through and is now shorting to something that it shouldn't? Is that going to cause a fire? Hopefully the answer is no. Hopefully you also notice and then fix it before the other wire wears through and then start shorting out on things. But if you grounded your chassis and your 12-volt, your positive wire had gotten scuffed and had exposed copper, and then it could start arcing to your frame, and bad things could ensue. So don't ground your chassis. When you're wiring up your throttle, think about what happens if one of the wires gets disconnected, comes loose, breaks, whatever. Prefer to have it fail safe and not wildly accelerate, general concept. That's why e-bikes generally use Hall effect sensors for their throttles that have a couple of interesting characteristics. One characteristic is that when it is at idle, it is not at 0 volts. It's actually hovering at a slightly higher voltage. The motor controller can use that to determine is my throttle plugged in? Good thing. It also, wide open throttle is not the full voltage rail. They're generally 5-volt throttles. Wide open voltage is like 4.5 volts. Again, the motor controller can detect if there's just 5 volts being applied to throttle. Maybe there's a fault with my throttle and don't wildly accelerate. And then there are linear range in between there, and so you can tell if the signal wire gets disconnected and is floating, there's probably a pull down in the motor controller. It goes to 0. It says, my throttle's not connected. I'm not going to wildly accelerate. When you're talking, if you've got a resistive throttle, the other option instead of Hall effect is a 5K ohm potentiometer. If you're wiring that up, the most safe way is to actually only use 2 terminals of the potentiometer. If you use all 3 terminals of the potentiometer, 5-volt signal ground, then you've got issues in that your controller can't detect whether it is shorted to ground or shorted high, or if something has come disconnected and it's confused. The way that you actually want to wire that up is that you only want to use the wiper and one end, because if a wire failed, a wiper in one end and it's wired in such a way that 0 ohms is idle and 5K ohms is wide open throttle. Because if a wire breaks, you're going to be at 0, other way around. If a wire breaks, you're going to be, you do want to do that. You want to detect if you're at infinite ohms. Because if you're at infinite ohms, the wire is broken. If it is shorted, you want that to be idle. And then if you're at anywhere in between there, you want to use that as range. But generally, you buy a motor controller and it says, I would like a 5-volt Hall effect throttle. And you say, great. You go on eBay and you buy a 5-volt Hall effect throttle and you stop worrying about it. It'll just work. If it says it wants a 5K potentiometer throttle, you say, great. You buy a 5K potentiometer throttle and you wire the 2 wires in and you call her good. You want to avoid a motor controller that has 3 pins for throttle and says, I want a resistive throttle. Well, that's a bad idea. Avoid those. Other thing about general safety is pre-charging. The motor controller has some big ass capacitors to make it not blow up. It needs them for smoothing and things. The problem is when you just plug in, if your motor controller's been sitting there, it'll have discharged its capacitors, and then when you plug in your battery, there's going to be an arc because capacitors really want to move a lot of current to stabilize voltage. So there's going to be an arc, and that's bad. So the preference is to plug in through a resistor for a bit, and then unplug the resistor and then plug in. That'll allow your capacitors to charge up through the resistor. If you want to get fancy about it, you have a resistor across your contactor, and then you plug your battery in, the resistor across the contactor pre-charges, and then you've got an aux switch that you can switch that then engages the contactor. And so during normal operation, you aren't running very much current through that resistor, but you do pre-charge. And again, this will make a whole lot more sense if you're actually looking at a schematic and saying this is how we're wiring it. Other thing in safety is connections. First thing about connections, do you solder or do you crimp? Or do you solder your crimps? Don't solder your crimps. That's actually an inferior connection to either soldering or crimping. There's some metallurgy that happens there. Soldering has the disadvantage of becoming brittle. You'll have a very stiff point and then a ways out, and then next to that you'll have where the flex happens and copper work hardens, and if it's flexing there a bunch, it'll get brittle and it'll break. That's bad. If you look in the automotive world, everything is crimped. That's for a reason. You should probably prefer crimping to soldering. Just make sure you get a good crimp. I bought a sketchy set of Harbor Freight ratcheting crimps because they help give you a better job of actually knowing that you've got enough crimp, because you crimp until the ratchet releases. If you haven't crimped enough, it won't release. Prefer crimps. Scotch-Brite. Scotch-Brite's important. Dull things don't conduct electricity well. You'll have surface oxidation on pretty much any type of material. So if you really care about what you're doing, you take a Scotch-Brite pad, you shiny up the connector, you shiny up your terminal, and then you make your connection. And then you'll have less resistance there, because that's my next bullet point. Resistance equals heat. We're talking about relatively large currents, and relatively small resistances start mattering. You get heat at your connection point, and then your connection starts melting, or starts heating, or badness starts ensuing. So you want to make sure that you don't have any, you want to make sure that you have consistent resistance throughout your whole power distribution, so you don't have any hot spots. Final note to mention, polarized connectors are good. Not being able to plug things in backwards is good. Common connectors that get used in the hobby RC world are XT60s. They're 60 amp rated, polarized male-female 2-pin connector thing. They're pretty good. They're actually solder connectors. They have little cups, you put the wire in, you solder, and that's what it is. I've been using bullet connectors on my e-bike because they were easy to acquire, because I could go to a hardware store. The trick is that all of my positives have the female of the bullet, and all of my negatives have the male of the bullet. And so while I can plug my battery into itself and short it out, I can't plug the battery into the motor controller backwards, because the motor controller, when it expects for the source, on the source side, the pluses are all females, the minuses are all males. On the other side, where the current is going to, it's obviously reversed so that it can get plugged in. But I can't plug it in backwards. Polarity is good, but fewer screw-ups.
What about Anderson?
Anderson connectors are also polarized. They
No, they're on the floor.
We use them in the project, but it's still not tall XT60s.
This is an Anderson connector. It is made by Anderson Power Products. It is a polarized connector by virtue, well, it's a polarized connector in that the other thing can only go in one way. This happens to be a 175 amp rated Anderson. They make them down,
Pretty small.
the FRC team uses 40 amp
We use
Andersons.
them on the printers.
You can get them up to 400 amps. I know. I've held a 400 amp Anderson. So that's a hefty connector.
I think that's one that's actually got a handle on it.
Technically, no. Can have a handle. The holes are actually so that you can either
There might
mount.
have been another one. When I worked at the post office, we had on battery powered equipment.
Yes,
Yeah, some of this size will have
they
handles on
probably
it.
will have a handle mounted to them, but it's not actually part of the connector.
Oh,
It's
okay.
just bolted on. So generally with like an Anderson like this, on one side, this is going to be bolted to the frame of the vehicle, and the other side is going to have a handle on it that I push in. And that's actually how a lot of forklifts do their final safety disconnect. Is that you got a big ass handle on your Anderson, and if you pull that, it gives you enough leverage that if you pull that, you're unplugging the battery. These guys are kind of nifty. They're kind of expensive, but they kind of do their job well. You kind of don't want to skimp on safety. But yeah, these are nice. They're also Chinesium off-brands. You can also cut these off the forklifts. Actually, for reference, this is one of Banshee's packs. This is a 36 volt, 40 amp hour lithium iron pack. I think that's all the more I want to talk about safety. Safety's good. Don't catch yourself on fire. Don't short things out unless you need to. Case studies. This is where I talk about things that I've built previously. Banshee, as a number of people are aware of, was a Power Wheels vehicle. Banshee had a 36 volt lithium iron pack, 40 amp hours. We pushed it to do 10C discharge. Might have been over pushing those cells, but we didn't really care because reasons. Technically, it was a 24 volt motor. We were running at 36 volts because we didn't care. It didn't explode. It was actually one of the few motors in the series that was properly rated for what we were using it for. It had a glorious like 2 kilowatt 1 hour rating. Other people had 2 kilowatt scooter motors. Those were like 2 kilowatts for like a minute. Ours was 2 kilowatts for an hour, which meant that when we were peaking 12 kilowatts through it, it didn't care. We had a 36 volt 400 amp motor controller. It was a Curtis branded motor controller, which Curtis does a whole lot of forklift supply. The motor itself came from a hydraulic pump on a forklift. We happened to have access to scrap forklifts at the time.
We still got a few of those.
We still got some contactors running around.
That's what I was thinking.
With the big wheel, it had a top speed of about 42 miles an hour. With the small wheel, it had plenty of torque. It could do burnouts all day long. There was no BMS. We did a bottom balancing on the cells. Once the cells were balanced, they were a pack. We never touched anything other than the top and the plus and the minus. It did have fuses. It was properly fused. The fuse was actually in the pack itself. One of the jumpers between the cells, instead of being a piece of copper, was actually a fuse. That's actually kind of the easiest way to do your fusing. That way you don't have to worry about any wire runs causing problems. It's just in the pack. If your pack stops producing power, that means you probably abused it pulling the fuse. But, our packs lasted approximately 45 minutes of hard racing. So that was pretty good. I mean, it wasn't forever, but 45 minutes of hard racing.
That's a good race.
It's not, and racing is a little bit different in that it's either idle, it's either no power or all of the power. So we were kicking those cells in the shins. By the end of its life, because of the ovaling out of our kingpin bolts and the hella stance that we had on the front wheels and the amount of scrub that we were doing on the tires, packs were only lasting about 30 minutes. There's a noticeable increase in battery consumption because of additional drag. There's also a noticeable increase in lack of rubber on the front tires, but you know.
Back tire kind of lost a little rubber.
Nah, back tire never was a problem in racing. It'd do burnouts if you held the front brakes. It wouldn't do burnouts just sitting there.
I know that, but I mean, the burnouts were
Oh, I mean, we
a little hard on the tire.
abused the shit out of that vehicle.
It also hurt when you flip it upside down.
Yeah, don't do that.
Do what?
It hurts when you flip it upside down.
Oh.
It also hurts when you run it into a barrier.
Tires.
Sometimes those things were combined.
Yeah, it really sucks when your brake pad decides to leave the vehicle.
Only if you want to brake.
Well, when you're coming off of the straightaway.
You need to make the turn. It comes in handy.
Coming off the straightaway, you need to make a hairpin turn. It kind of helps to have your brake pads on.
That and you don't run into somebody else.
The Tuk-Tuk is another silly electric vehicle. It used two 36 volt 40 amp hour lithium iron packs in parallel. It was not doing the right thing of paralleling first and then seriesing because we just didn't care because the packs were balanced. It actually was using the same packs that Banshee was using. Took the pack out of Banshee, put it in the Tuk-Tuk. It has a 36 volt 400 amp SEPEX motor controller combo that came from forklifts. Again, a Curtis controller. It has stupid low gearing, stupidly low. It only has a top speed of about 30 miles an hour, but it has all of the torques.
Yeah. It pulled a full-size pickup truck up a hill with it.
I don't know if it was up a hill. I think that story is getting exaggerated. A slight incline.
It was up a little bit.
There's some incline.
Hey, there's some tires on that puppy too.
Yeah, the Tuk-Tuk has all of the torques. Technically, it is a motorcycle. This is a three-wheeled vehicle. It does actually have a VIN somewhere, probably. At least according to
Well, we had the paperwork.
Technically was a motorcycle.
Yeah, we haven't actually told anybody that we've done the electric conversion on it officially, so don't worry about it. It
I
has
would just change the rules on it.
it has some range. We don't know. Some.
Hey, we got it all the way from down there north of the post office, the Science Center, and back.
Yeah. That's some. Non-zero. The mini bike. The mini bike had a custom. I think it was a 13S. It might have been a 12S. I know it was a 4P lithium pack, so it was running about 48 volts, 10 amp hours. It was using an alternator as its motor. It was a Kelly motor controller, one of their censored controllers. I think it was the 400 amp peak KBL series. I think. I might be misremembering. It had some top speed and it had some torque.
About 23, I was thinking, for speed.
Okay, I never measured it. Some.
Somebody's said 23, that's all I can say.
Some. It had some. It would get up and move. It was plenty. It was plenty.
It had a fair amount of range too.
Yeah, it's some.
You get down to the sculpture garden and back, usually.
Yes.
If they charged it
The
enough.
sculpture garden's not that far away.
Yeah.
It had some range. It had some torque. It had some top speed. It was a fun little vehicle. Recently I built a sketchy bike. It's very sketchy. It is technically a 12S3P pack. Each of the P's is a 1.5 amp hour, and so 48-ish volt, 4.5 amp hour. It's got a 48 volt 1000 watt e-bike kit, which means that motor controller peaks at about 20 amps. Top speed of something, maybe, kind of, approximately
Downhill.
30. I don't know. Downhill with the wind at my back. It doesn't have enough torques. I wanted something to be more torquey, but realizing that I should have known it when I went into it. It's perfectly serviceable. Like, it works fine. Like, it's a thing. It does what it's supposed to do just fine. But when I build an electric vehicle, I want to not use all of my throttle. I want to use it once and say, you know, that's good. I don't need that. But that's good.
And a lot of that has to do with the type of motor you're using.
Yeah.
So, do you know if your hub motor is direct drive or is it geared?
I think it's geared. I don't know. It's a thing.
Yeah, some of them, if you get a geared hub motor, then you can multiply your torque, obviously.
Yeah. But you wasn't what your top speed is.
So you would have liked to have had a larger wattage?
Yeah. I mean, really a bike is not the form factor for when I really want a sketchy electric vehicle. Too high up, it's too proper, it doesn't look derpy enough. I mean, all of these things.
You're pretty top heavy too. I mean,
Yeah.
it gets
Yeah.
a little shaky on some of the roads.
I want fat tires that are low to the ground. I want small fat tires so that I can have lots of contact patch and not much gear reduction.
Oh, you want like that scooter I was looking at?
Maybe like a drift track. Maybe like a go-kart.
Yeah.
I mean, it was perfectly serviceable. What it is, how it rides fine as a bike. It just isn't a silly enough electric vehicle. But I have high standards for my silly
It
electric
doesn't
vehicle.
really have the silly factor.
No, it doesn't have a silly factor. It's perfectly reasonable. It's a perfectly reasonable electric vehicle.
How'd you wind up with that?
I don't know. I failed. And so that's all the more presentation I have. So,
So how does the amp hour, how do you get amp hours? Like you said, you had 3 packs that were 1.5 amp hours. What determines the amp hours?
the cell, the manufacturer's stamp on the cell. I mean,
Okay, so can they all be 18650?
they're all 18650 cells.
But, so you just gotta figure out, how do you figure out if you have a pile of cells?
They should have markings on them. Should.
Should be some kind of
There-
a model number.
Yeah, there should be a model number and a capacity rating on them. Unless you got super sketch cells. If you got super sketch cells, then I wouldn't even trust that. The other way that you actually know what your capacity is you get a proper battery meter and you discharge it to a known voltage. You then charge it with a known current and you measure the current as you're charging it until it gets full, and then you know you coolant count. You charge it. So if I charge a cell at an amp for an hour, I've got a 1 amp, and it's full, I've got a 1 amp hour cell.
There's still a lot of these people with their battery kits or building battery kits that will say 13 to 20.
For
It's
the
not-
amp hour.
It's not more batteries, it's the rating of the batteries.
Yes, yes. An 18650 cell on the low end, if you're looking at a power cell, one that has a high C rating, you're probably buying them in the about 1.5 amp hour capacity, which is actually the Samsung INR 1500s are what are in the Cobalt packs. They're 1.5 amp hour. That's about the lowest amp hour 18650 I've seen around. Most
They
of
do have a good C rating.
Oh yeah, they got a great C rating on them to make up for that. The most 18650s you see, you can get fairly good C ratings in a 2 amp hour. You kind of get a balance of a 2.5 amp hour, and about a 3 amp hour are the ones that are a low C rating, but they're the most capacity you can shove into that. If someone claims to have more than a 3 amp hour 18650 cell, they're lying and trusting that you don't have the equipment to measure their lie.
So how are they,
But
is there stacking them up to get the, I mean,
yep, yep,
More in parallel.
yep, more in parallel.
that also brings up the amp hour rating?
Yep. Oh yeah. Yep. When you put them in parallel, when you put them in series, their voltage adds.
Right.
When you put them in parallel, their amp hours add.
Okay.
And he was
Yep.
stacking them in threes. So we got
Yep.
4.5.
So I took 3 1.5 amp hour packs and put them in parallel, and so 3 times 1.5 is 4.5. My voltage didn't change. And then I took 2 of those Franken packs and put them in series, and so instead of having a 6S, I had a 12S.
Something that concerns me on eBay, there's somebody selling Samsung sleeves.
Oh, yeah.
Yeah.
To put over somebody else's battery?
Oh yeah.
Yeah, because there's
They're shrink wrap.
thousands of
I mean,
screwball China batteries.
Yeah, yeah,
out
yeah.
there.
So an 18650, the blessing and curse of an 18650, they are a common form factor.
Known entity.
They're a known entity for sizing, which is great. The downside is an 18650 needs protection. It is not mechanically good. You aren't gonna. So double A's are the same way. Double A's are not mechanically good. They need to be protected by things. When you have something with double A's, it goes into a hunk of plastic, and that hunk of plastic protects it, gives it mechanical stability and protection. Same thing with an 18650. The only thing that's keeping an 18650, the only thing that's keeping an 18650's positive lead and its negative lead apart is not that much. About an 1/8 inch on the top of the cell.
Yeah.
The
So
outside
you gotta
shell.
remember, yeah, the outside shell.
The
is
outside
negative.
shell is negative. The entire outside shell is
Yeah.
negative. That sleeve on there is that the reason there's that shrink wrap tube is for marking and to make it not short out. But it's not a very thick sleeve.
Mm-mm.
So mechanically, you can nick that sleeve, and you can very quickly get yourself into shorting things out that you didn't expect to be shorted out.
Okay.
Yeah, that would be bad.
Yeah.
On the counter side of things, this pack of Cal lithium irons, they've got an 1/8 inch of plastic around. At least, yeah, like they're a fairly hefty amount of thick plastic. The cell itself is ruggedized to such that it's fine. Those cells, their connector is a tapped M8 hole. You thread an M8 bolt into it, and there you go. That's how you connect to it. What's this? Welding? No. You grab some copper pipe, you hammer it flat, you drill some holes, and there you go. There's your battery strap. It is sketchy, but it works.
There's a guy that's taking 1/4 inch copper pipe
Yep.
and he's rolling it flat.
Yep.
And he takes a little buzzy spinny grinder thing, Dremel. Takes a Dremel and he lays it up beside his batteries in his deal. He takes a pencil mark and he just runs a line through it and just lays his wire through there and solders into his batteries and I was like,
I wouldn't solder.
yeah.
So I would go on eBay and buy me some tin copper strap.
Yeah, the straps are, yeah, then you can
and-
spot weld that.
And you spot weld it,
Yeah.
and it's good.
Oh, okay.
We've got some strapping. We're gonna need it. If we really start building more e-bikes, we're gonna need to buy more strapping.
Yeah, I was actually gonna buy a roll of it.
I was gonna say,
Yeah, I'll
roll
pitch
can't
in
be
for
too
that.
bad, is it?
No, I don't think they're too bad.
No, they're pretty cheap.
But yeah.
Same size as what you used on the.
I don't know who
Yeah.
has good stuff and who doesn't.
How
you know,
much
so.
was your?
Yeah, there's a couple of sites. There's
Mine
one.
I bought
There's a
was
site called lunacycle.com
Huh?
that sells
200? Or no,
pretty
one-
nice looking e-bike
179.
parts,
Yeah.
but they're not cheap.
No.
And
You
they
feel much
changed the
environmental
motor
good.
ratings.
Yeah.
They're on their website. They're advertising.
Is it
up
doing
to
copper,
1200
nickel,
watts.
steel?
I don't know exactly which
strapping.
one I got.
Yeah,
For the strap.
Battery strapping.
Yeah.
I think it's probably nickel.
Well,
the stuff they use.
Well, I mean, I thought that's what we
What is
used,
it?
like on the pack for the little two-wheeler.
The site talks about how long they've been in
something
business,
played it.
but their business
Oh, is it?
practice
Oh, okay.
is not
No,
good
I'm trying to remember.
for a site that's been in business.
Maybe
for
nickel-plated copper.
Or however
I
long
think
they
so.
claim.
well,
I think you can hit stop on that. I'm done rambling.